Hi everybody, I'm Max. I'm presenting, now that we've been thoroughly scared of static analysis of dynamic languages, we're going to do a little bit of work into how you don't do static analysis of Python. It's a project I did with CF, who's here as well. It's called Dr. We Notice because we have information about the type signatures, we notice. This is an SNL character. So we're going to talk about the state of Python and the C extensions that are commonly used. We're going to talk about why this bites in PyPy, a fast Python runtime. We're going to talk about how we made it faster in PyPy, and then how this sort of affects the broader dynamic languages ecosystem. So Python is a very widely used language. It's got a bunch of applications, mostly to glue C libraries together. So that's the CPython logo. NumPy is a big library for math. It's widely used in Python. Blender is a big C application that embeds Python. And Qt is a GUI framework that has Python bindings, so you can build C++. You can use in C++, but you can also bind from Python. Because CPython was not designed for performance, the call for performance came, and the developer's answer was, oh, just write a C extension for the hotspot of your program. So that means over the course of 30 years, you get a bunch of C extensions to Python, and then eventually at some point was realized in this official C API. So you have this PyObject star type, you have a bunch of other types like PyLongObject, you have a bunch of official functions, and that's the C API. When I talk about the C API for Python, it's this. And we'll see more about that in a second. And it's kind of like the JNI, but it's a little different. The JNI was designed from the get-go, I think, to support multiple JVMs. The C API was just CPython. So let's take a look at an example C API function. This is PyLong as long. This takes a PyObject star, which is the Python heap object, and it converts it to a C long. So you call this when you have an object and you want to unbox it. And there's some documentation for it. And then part of this, the contract for this function is it'll raise an exception if it's too big, or if it's not an int, or some other error happens. It'll return -1. It'll write something to the Fed local storage, and then you have to read from the Fed local storage to disambiguate if your thing was actually -1, or if you got an exception. Fine. But that function sort of assumes some stuff about how CPython works, about how the Python works. PyObject star is a CPython object. It does not move. They are fixed for eternity. And they also assume that you have all these other functions like PyErrorOccurred implemented in your runtime that just read from thread local storage. It doesn't take any parameters. It doesn't take a thread state. It just has to look it up. And there are other Pythons like PyPy. PyPy's goal is to make Python fast. It has a really advanced JIT, about 20 years old, 20 years of research in there. And it does support Python C extensions, but it has a totally different object model. So because the CPython C API was developed for CPython, and PyPy is a different object model, it's got a moving GC. Objects just move around. And it also has a totally different object layout, right? It's not PyObject based. It unboxes things sometimes, or when it does box things, they have totally different memory layouts for performance reasons. You don't have PyObject star. You just don't. So it has to emulate PyObject star and all of these other functions, and that bites. That really hurts for performance, and also it's just a lot of code to manage. Here's an example of why it hurts for performance. You might be in the JIT running some Python code. It's an optimized trace, and it's basically unboxed all these numbers, and everything's fine. And then you call a C extension function. And you know it's a C extension function, so you have this whole path of stuff to talk to it. And the C extension function speaks C API. It does not speak PyPy. So, okay, you're in the JIT, you pass it a number, you box the number into a PyPy heap object, and then you say, okay, well, we have to make a C API object, PyObject star, and then you pass it to the C extension. The C extension, its interface generally is you pass it an array of objects, and it parses them itself. So then it goes and it unwraps the PyObject star, it does something, and then it returns a result. And the result, it boxes to fit the C API contract, and then that goes back to PyPy, which unwraps the PyObject star into its heap object, and then it goes back to JIT code where it unboxes the integer to a C integer. And that's a lot of administrative overhead. That sucks. So let's take a look at how that works for a very, very, very simple example. You have a C extension. It's called AC extension because I'm very creative. It has an inc function that takes a takes an integer, and it increments it. It returns a new integer with 1 added to it. So this is Python code. This is C API code. You can tell because this one has curly braces. And the way you register your functions is you have this array of structs, and it's the inc. So you've got an inc string, and it points to some function pointer, also called inc. And it has this thing called meth_o, which I've bolded. You don't need to worry about the specifics, but meth_o says it takes 1 argument. Okay. And the manual argument parsing this is what this looks like. There's this required boilerplate where you say, here's the 1 argument, unbox it. Maybe something happened. It wasn't actually an int. Maybe it's, out of range, blah, blah, blah. You propagate the error, you return null. And then you call the bolded stuff, by the way. This is the only real work in here. You call your real work function, which adds 1, returns, and then box it again. Okay. Very small amount of real work for a large amount of overhead. For more arguments, it's even worse because you don't have these variadics that, you don't go C variadic. What you do is you pass an array of PyObject star, so PyObject star star. We're now 2-star programmers, and then the number of arguments. And then you go through and did you get the right number of arguments, pull out on the thing, extract a float, blah, 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 blah. Do your real work of adding 2 doubles, box it. Even more administrative overhead. Really, really fun. This is what's called meth fast call. It's fast because in CPython, you don't allocate this array. You just take a view of the stack, which is all PyObject star. And that's the core of this, is that PyPy already knows this stuff about its objects. Why would you need to parse the arguments? If you already know this stuff, you already know things are ints from your traces. There's this really advanced optimizer doing all this static analysis. But none of these checks are visible to PyPy because they're all in this, this is this thick line here. This is C extension code. None of it is visible to PyPy. This all happens in this opaque blob that PyPy can't see into, so it can't remove the checks. It just has to call into this thing with this contract, this C API contract, and you lose. Bummer. So it has to manufacture this PyObject star because it can't do anything about all of these checks and all of these interfaces. So we said, all right, you could do a bunch of static analysis, or you could add types. You say, here's a type descriptor for this inc function. It takes 1 C long, and that's an array that's terminated by -1. And you return a C long, and the underlying function is this thing called incl, which is doing the real work. And then you sort of stuff it behind the name. So instead of putting a string literal, you say this is the inc field, and then if you have this bit set, the meth typed bit, look behind the string. There's some types. And the nice thing about this is since it's stuffed behind the string, it doesn't actually break any API. You can't expand the struct because that would change the size of these arrays, and other Python implementations and CPython and stuff would break on these C extensions. So that's cool. And then once you have these types, the nice thing is you just use them in the JIT. So you read that struct once you load the C extension. You say, okay, this function pointer, you pass it 2 longs, or you pass it 1 long, and you get a long back. Skip all the stuff. Don't box it. Don't check it. Don't make a PyObject star. Do not pass go. And this is what the code looks like. This is what the transformation of the code looks like. So previously, in the JIT, you might do something like, are you an int? Okay, great. We'll just do the unboxed thing. And because you have this nice fancy optimizer, you can say, well, we already know it's an int. Skip that check. Oh, we already know it's unboxed. Skip that. Don't need to box it either because it's just going right back into an unboxed int variable in the trace. So all of this stuff in the optimizer gets blown away, and you end up with this nice clean call. It's an indirect call still most of the time, or actually it might even be a direct call to a C function with unboxed arguments and unboxed return. So here's an example of a micro benchmark, and you can tell it's micro because this is the entire benchmark. You import a C extension, you call inc a billion times, and you measure. Did it get faster? This is the worst possible case. You have a tiny C function. It's all administrative overhead. Did we do any better? Let's see. Turns out yes. So this is a big box and whisker plot, but the things are very compressed because there's not very much variance. We have a bunch of Python runtimes. graalpy is on the left, 2 PyPys, 3.10, and then 3.10 that we optimized, PyPy 3.8, and then a bunch of CPythons. And you can see that there's some performance variation in the CPython. graalpy does pretty well, and PyPy 3.10 before our changes did terribly, like really, really abysmal. This is 160 seconds to do a billion ads. Not great. But after our changes, 2 seconds. That's pretty good. That's like 60 plus X speed up. Again, this is the worst case. This is not a real benchmark. Nobody writes code like this, and if they do, they shouldn't be writing code. But it's the worst case gets a lot better, which is pretty nice. And so the consequences for PyPy, you might say, well, does this break anything? How do I know it's correct? Blah, blah, blah. And it's pretty limited blast radius because it's opt-in. You have to add these types. If you don't add the types, it doesn't break. It also doesn't get faster. And so yeah, it's 60 to 80x, but on some benchmarks and only if you're writing code like that. But it's still, your effect radius in your JIT compiled function is much smaller. You can do a lot more optimization around the C calls. But if you don't opt in, nothing changes. No breaking, no performance changes. And then for other Python VMs, we see that in graalpy 22, things are pretty fast. But in graalpy 23, they dropped this thing called Sulong, and their runtime it actually didn't even finish in our benchmarks. So you run this thing a billion times, and graalpy 23 never finishes because they removed the thing, their technology called Sulong, which I'll talk more about in a bit, that makes this fast. So can we help other runtimes? I think yes. graalpy could use something like this. CPython doesn't need it yet, but they're starting to build a JIT. Right now they have it's called a copy and patch JIT. It's kind of a baseline JIT. But as soon as they start doing more advanced JIT tech, they're going to start unboxing objects, and then they're going to run into the same problem. So it will bite them eventually, and they could use these type annotations. So the takeaways from all of this is that optimizing across language boundaries is hard. Raphael knows that as well as anybody. And if you just add type information, you get a lot. You get a lot of mileage out of a couple annotations. And it doesn't break a lot. So I think the first implementation of this, we had 1 or 2 bugs, and then it was, it's only 60 lines of code, it turns out, and it doesn't break very much. And then if you don't want to add all these annotations, you don't have to, because the thing we're working on right now is, say you have Python code, which a lot of people do. Python is it's a different language. It's sort of 2 things. One, it's a binding generator, so you can use it to interface with existing C functions, or you can also use it as sort of a Python compiler. And the nice thing is it has these types, and I've bolded them because they're not normal Python types. They can be trusted. They are checked. You cannot lie to Python. And the nice thing is we can take those ints and generate the type stubs for you. So no need to write them by hand. Use Python. Your code automatically gets faster. That's fun. And that's it for us. Papers on ACM. This is a QR code for the paper. Call me, beat me, and this has been Dr. Wenowdis. Thank you.
Okay, thank you, Maxwell. We already have questions.
Hi, I just wanted to ask about I think it was like 2 slides ago,
Yep.
where you mentioned that it was like an opt-in, I don't know if that's the right slide. Yes, and you said nobody has this right now. Is that just because there's no motivation for, like, I guess because you haven't published it yet? Or I guess I wasn't understanding what that meant.
So it's not merged into mainline PyPy.
Okay.
The reason is twofold. One is, writing the types is kind of onerous, and we'd rather generate them from Python. And the second thing is we're working on a sort of more expressive type protocol. So right now, what you can say is you can promise, you pinky promise within the type information, this function never raises an exception, and you get, no exception checking. But that's kind of or you can say, well, it might raise an exception, and then PyPy has to check. But we'd like to have more stuff there. Like maybe it's not reentrance at all. Maybe it's you know, I don't know. You can express memory effects somehow. So there's just more work we want to do before merging it.
Thank you so much.
Any more questions?
Thank you for the really interesting talk. I was wondering, so the types in Python are complicated.
Yes.
So are you mostly handling the nice underlying C types, let's say, or what are you targeting in this area?
That's a good question. Right now it's just C types because the perf hid is in unboxing and all this other stuff around them. And if you're passing in a Python object, then you're probably going to do weird Python things to it. So you're going to take the perf hid anyway in the C extension. But there's some stuff that you can do, like if you promise you never get, I don't know, you might, you know, the exception stuff still, like maybe you never raise, you can guarantee somehow you wave your hands, you never raise, you can avoid some TLS lookups, but right now it's just C types. Well, there's also none. We do support none. You can say the return is always none. Great.
Any more? Okay, thank you, Maxwell.
Thank you very much.